In this playlist, I'm going to try to review one of my old exams. This is for Thermodynamics 1, Exam 1. And my purpose is to solve the exam as example problems, but also talk about test-taking strategies. So in this first video, I want to read through the whole exam. I want to look a little bit on how I would approach this exam and also how I make exams. So one thing that might be helpful is if we look at this document. This is the Exam 1 scope document. What I do is I tell students that these notes cover the topics that will be in this exam. This is the first out of, I believe, 2 midterms and then a final exam. And this exam is mostly on the first law of thermodynamics. So I have a list of calculations as well as concepts. I'm not going to go through them in detail because most of the people watching this video will be students in my class and they know this document already. But I thought it might be interesting to step through the exam and see how good a job I did of covering the scope of the exam. It really should cover most of the topics, although admittedly, I don't know that this document existed in this form in 2018. Well, let's find out. In terms of test-taking strategy, I strongly recommend that you read the whole exam before you decide where to start. And remember that you want to train yourself to get as many points as possible in the shortest amount of time as possible. And so my grading system is designed so that you'll get 6 out of every 10 points by showing that you understand the setup and the concept behind each problem. And then the remaining 40% or 4 out of 10 points is showing that you can crank out the numbers, which I think is important, but not as important. Let's look at problem 1. We have a van der Waals gas, and its internal energy follows this formula, where gamma is some unknown constant, A is a constant in the van der Waals equation, and this is a curveball. So this is not something that would have been presented in the notes. It's some weird formula for internal energy, and what we're asked to do in part A is calculate CV, and then part B, we calculate H, and then we look at this gas in a piston, and we're asked to set up the integral to calculate the work for expansion from V1 to twice the volume. Okay, so what topics are we covering here? Well, this is a closed system, at least it is in part C, and we're talking about work, expansion work, we're talking about enthalpy, we're getting into the calculus of thermodynamics. So I would say most of the items on this list are covered. Underlying concepts, I think you do have to understand what temperature, energy, and heat capacity are. Well, it touches on extensive versus intensive variables. We don't really talk about the Gibbs phase rule, but U and H are state functions. We are talking about the van der Waals equation of state, which I guess is related to the ideal gas equation of state. So I think we're covering many of the topics on the list. Let's look at problem 2. So glucose can react with oxygen to produce carbon dioxide and water. And it releases heat, given here. And we have a table of standard heats of formation. And we're told we burn 2,000 kcals per day. How many grams of glucose would we need to consume? It looks like we're given the heat released upon oxidation. So this should really just be dividing these two numbers. well, I'm not solving the exam right now, but that should be just calculating how much glucose to consume in order to release a total of 2,000 kcals. And now, what is the heat of formation of glucose? I presume that's not given in this table. Sure, it isn't. And we need to neglect sensible heat effects. So we just need to determine the standard heat of formation of glucose. We're given the heat of the reaction and then the heat of formation of the other compounds except glucose. So this problem, oh wait, let me read the last part of the question. The reaction results in 1 mole of CO2 produced, and the gas is collected in a bag. The surrounding pressure is constant at 100 kilopascals. So how much work is done as the gas fills the bag? So that just should be this pressure times the change in volume. Coming over here, I think we're covering some of the same topics, but we are covering heat effects, heat of reaction. We are not covering sensible or latent heat, although those are kind of implied in the question. And so far, property tables, those are covered. We're not covering phase diagrams, but it looks like the exam seems to be reasonably appropriate given the scope. Okay, so notice that problem 2 is very different in style to problem 1. It's more about cranking out numbers related to enthalpy than sort of theoretical or calculus-based thermodynamics. So you may prefer to do number 1 or number 2, depending on your own feelings. Let's see problem 3. Okay, so we have a tank with 20 kilograms of water at 25 degrees C. It's a liquid. And then suddenly 2 inlet valves and a single outlet valve are opened. The 2 water streams flow into the tank. You have 4 and 6 kilograms per second at 80 degrees C. They conveniently gave you a diagram showing how the stirred tank looks. And the output, M3, the mass flow rate of the output, is not specified here. And what it's asking, in problem A, it's saying calculate the mass flow rate at steady state of the effluent. So that would just be the sum. Well, again, we're not solving the problem, but it would be M1 plus M2 equals M3 in equals out. Now in problem B, in part B, we have the energy balance of an open system. This would have been given in lecture. And the energy balance does not assume steady state, but now we're asked some conceptual questions about what these terms mean. So which term in the energy balance would be affected by the following phenomena? The work done by fluid pushing against the outlet pipe, steam flowing over the outside of the tank, that would give you a heat input, an impeller stirring the tank, an expansion or contraction of the tank. So we're asked which of these terms are affected by each of these. That's a conceptual question. I like those because they can be short, or at least fast to answer. Now calculate the temperature of the water in the tank at steady state, neglecting heat exchange with the surroundings or changes in gravitational potential or kinetic energy. Assume the tank is well stirred and that we have work put into the stirring. So that is some work input. And that is the only work done on the system other than the work of flowing the fluid in and out. And then the heat capacity is to be treated constant. And remember, we want to calculate the temperature at steady state. Now we derive an expression that would give you temperature as a function of time. So that involves a transient balance. Okay, so this one is maybe more, more mathematical than the other two, or involves a differential equation. This one is, I would guess, probably less of a curveball relative to what's in the homework. And this one is kind of a curveball. And I would probably recommend that most students start with problem 2 because it's more comfortable. Give yourself a little bit of time to warm up before you start addressing the curveballs. I personally would start with number 1 because I love thermocalculus questions. In the next few videos, I'm going to make one video for each problem. And what I recommend doing is write out the math in abstract terms first and show that you know what you're doing and that you know what calculations to do. But in my opinion, actually cranking out numbers should not be your priority until you have answered at least the setup of every problem on the exam. But since I want each video to stay with one problem each, I'm going to first write out what I would initially write, and then I'm going to do the math. But what I would actually do if I were taking the exam is I would set up every problem for the whole exam before I actually got out my calculator and started doing calculations. I want to also point out that students in my class would have an equation sheet that hopefully makes it so that they don't have to memorize things. And I will be including this equation sheet on the screen as I work through the problems.